5.1, day 2, talking about log properties. The first log property, we're going to call it the product rule. And it pretty much says if you're taking the log of a product, two numbers, we'll say A times B, then you can actually split that log up into a sum. So you can write it as the sum of these individual logs. So it would just be log of A plus log of B. That's all the product rule says. If you're taking the log of a product, you can split it up and write it as two individual logs, their sum. So let's do a quick mini example to illustrate that. So the directions are just to expand. Or another way you could say it is write it as a sum of two logs. So we have log base 3 of 6x. So since we definitely have a product inside the log here, 6 times x, we can just write it as log base 3 of 6 plus log base 3 of x. So notice it still has the same base as it started with. So log base 3 of 6 plus log base 3 of x. And we also could have gone backwards. If we started here and we wanted to write it as a single log, write it as one big logarithm and then 6x on the inside. So we can go either way with the product rule. Okay, next rule. We did the product rule, so we got to do the quotient rule, of course. And that one comes pretty naturally. If you got the pattern down for the product rule, you could probably guess what I'm going to say for the quotient rule. So if you have the log of a quotient, which means something divided by something else, we'll say A divided by B. You can write that as two individual logs that are subtracted, so it's the difference. And remember, order matters here, so A divided by B. So when I say they're subtracted, you do log of A minus log of B. Okay, so an illustration of that. Now we're going to go the other way. I'm going to say condense. So you're going to write it as a single logarithm. I'm going to give you log base 4 of z minus log base 4 of 8. So if you notice the bases match, and you're subtracting two individual logarithms here, you can write it as one big logarithm. So it's log base 4, keeps the same base, one big logarithm, and then it's z over 8 inside there. One thing I want to stress, the word log is only written once here. It's not log divided by log. So if it's two individual logs subtracted, it's one big logarithm. I should only say the word log once here. In the third rule, we'll call it the power rule. So this one's important. If you have the log of something that's raised to a power, so it has an exponent, this rule says that you can take that exponent and put it out front. So in this case, the exponent's t. We can just take the t and put it out front. So I always kind of just circle it and draw an arrow out front to show that that's where I'm going to put it. So that's the power rule. And technically, it could go the other way too. If you had a coefficient here, you could definitely put it back up top on the exponent. So, an example of that, I want you to expand, which means flatten it out completely, log base 5 of x to the 4th. Well, there's really only one thing we can do here. X to the 4th, we'll apply the power rule here. Take that 4, put it out front. And there you have it. So now the 4 has just become the coefficient in front of the log. So it's 4 times log base 5 of x. Okay, example 1. I just want you to expand completely. So whether it means write the log as the sum of two logs or the difference of two logs, I want you to expand it out completely. So part A is log of 8x times y to the 4th. So if you'll notice, there's three pieces in there. 8 times x times y to the 4th. So we should start by, if we're going to expand it, do the individual logs, do their sum. So log 8 plus log of x plus log of y to the 4th. And then a lot of people lose points because they just leave it here. But the directions, since they say expand completely, we're actually missing the last step here. We need to take care of this 4 on the exponent. So let's apply the power rule here. Take that 4 and put it out in front of this log. And as long as we take care of that, that one is expanded completely, so we're good there. And then part B. The ln, the natural log of this quotient here, square root of x squared plus 5 over x. So don't forget, the ln is just a fancy way to say log base e. So it's a log just like any other logarithm. So the same exact rules apply. And since we've got a quotient, I'm going to start by breaking these up into like a subtraction of 2 logs, the difference of 2 logs. So that's the ln of the top part minus the ln of the bottom part, right? And then just to simplify things a bit, I want to take care of the square root. So we've done enough of this by now. You know the square root is the same as the 1/2 power. So x squared plus 5, I can raise that to the 1/2 power. It's the same thing. So that's what I'm going to write in there. X squared plus 5 to the 1/2. And then this one was just x. And the reason I do that in this step is because since I need to expand completely, there's still one thing remaining that I need to take care of. So don't leave that as a square root in here, because since that has an exponent of 1/2, the last thing we need to do is take that 1/2 and put it out front as the coefficient. So as long as you can put that exponent out front, move the 1/2 out. So it's 1/2 times the ln of x squared plus 5. And then you have minus the ln of x. So that I'm good with. There's nothing else we can do on that one. Okay, then the last example we have here. Log of the cube root of x over y. The reason I want to show you this one is because I want to talk about the order that you do things in here. So I can't apply the quotient rule yet because this whole thing's under the cube root. So we need to take care of the cube root first. But we know that's just the 1/3 power. So instead of x over y cube root, let's just call that x over y to the 1/3 power. Well, now you see we can take care of that exponent. Let's use the power rule and put that as a coefficient out front. So I have 1/3 times the log of x over y. And then since we're going to expand it completely, we need to take care of this quotient. That's an easy one to take care of. You have log of x minus the log of y. But then I want to be careful with the final answer, and I'll show you. This 1/3, it needs to stay out front, like outside the parentheses. And I really want to stress that there's parentheses here. So log of x minus log of y. And the reason I stress that there's parentheses here is because this 1/3, it has respect to both log x and log y, right? If you think back to the beginning, it had a cube root on the x and the y. So this 1/3, that's why it should be outside the parentheses, like it's ready to be distributed through. So it's 1/3 log x minus 1/3 log y. And if you left it like this with the parentheses, I'd be okay with that too. If you left this as your final answer, that'd be fine. But just to show it, I went ahead and distributed it through anyway. So you know that the 1/3 really has respect to both of these. But if you forgot the parentheses, you would only have the 1/3 on the log x. Like it would look like this one. But in this case, the 1/3 should be on both. Okay, and now I want to go the other way. So I want to give you a couple cases where you can just go backwards and write it as a single log. So part A is 3 ln of x minus the ln of 2. So that's natural log. Those are just logarithms. The first order of business, we can't combine these logs just yet. The first order of business, you need to get this coefficient out of the way, this 3. So that's a big distinction here. Before you can combine logs, you need to make sure those coefficients are taken care of. Well, that's an easy move. Just take it and put it back up here on the x and make it x cubed. So that's the first order of business. Take the 3, put it back up on the x. So I got the ln of x cubed minus the ln of 2. And now you can go ahead and write it as one big logarithm. So you have the difference of two logs. They're the same kind of log. They're both ln. So we can write this as ln, one big logarithm. So I should only see the word ln one time, and inside that's where I see the fraction. So it's x cubed divided by 2. Okay, so that one is written as a single log. That's good. Part B, 3 times the log of xy minus 2 times the log of yz. Notice that's a product inside there. So again, before I can write this as a single log, I got to take care of these coefficients, which is easy. Just do the power rule. Take them and put them back up top on these exponents. So take the 3, put it up top. Take the 2, put it up top. And we're left with log xy to the third minus log of yz to the second. And then since these exponents are on like the product, like x and y, or y and z, I'm going to go ahead and call this x cubed, y squared, z squared, because it's cubing both of those terms. And this one's squaring both of these terms. So then the last step, log of something minus log of something else. Let's go ahead and write it as one big logarithm. And just make sure you have the order correct, which should be easy in this case. So x cubed, y cubed over y squared, z squared. And then the one note I do want to add, if you're going to combine logs together, they must have the same base. So they must have the same base to be able to combine. And the other move that we've already talked about is you've got to get rid of those coefficients first. Throw those back up on top of the exponent before you can start combining things into a single log. Okay, so the last piece we need to talk about for these notes is solving equations with logarithms. So let's start with an example. Example 3. 2 to the t equals 3,370,000. Okay, so before, in last chapter, if we wanted to know what t was, let's say it's time, like doubling time for a population, we would have to put this in our calculator, like y1 equals 2 to the t, and y2 equals this thing. And we do second trace intersect to see what t was. But logs are what allow us to solve for this algebraically. So now we have a way to achieve this variable that's in the exponent. So that's my point. That's what I want to start with. So to obtain the variable in the exponent, how do we obtain it? How do we get to it algebraically? You can take the log, or the natural log if you like that one better. I sometimes do because it's less writing. So you take the log of both sides. That's what we're going to start with. And that's kind of why I left myself a little room here, because I'm going to go ahead and take the log of both sides. So why would I do something like that? Well, if you remember the properties, one of the properties that has to do with the power, right? That allows me to go ahead, since I took the log of both sides, I've got log of this, I can go ahead and take that exponent out and bring it out front as the coefficient. So now I've gotten the exponent down out front. That's kind of the goal here. That's how I can access it. So that's the whole point, is use the power rule to move the variable. Like the variable becomes the coefficient. You can move it out front. Alright, so let's go ahead and take that t, move it out front. So now I've got t times the log of 2 equals the log of this big number. And log of 2 is just some weird decimal. I mean, you could get that in your calculator. So I'm going to keep things nice. I'm not going to put anything in the calculator yet. The last thing I'm going to do to divide, or to get t, is divide by log of 2 on both sides. Whatever nasty decimal that is, I'll get that in the end. So just divide to solve. So divide both sides by log of 2. So that cancels out here, and I just get t equals this quotient here. So if I didn't have a calculator, I would just leave it this way. This is as good as I can get. But if you throw this in the calculator, and make sure if you do, that you close the parentheses here, and it's divided by a different log. It's approximately 21.684. Okay, so now we have a way to actually solve for variables in the exponent. Take the log of both sides, variable gets to come out front, a little bit of division, and we're there. Okay, example 4, and this is the last example here. I've got 5 times e to the 2x equals 50, and the goal here again is to solve for x. Okay, the first order of business is not to throw any logs at this yet. Let's do the easy stuff first. So I always like to say, clean it up. Our goal is to get to x eventually, but the easiest thing to do now would be to divide by 5. So let's divide by 5. We get e to the 2x equals 10. So now we just have a base raised to an exponent, and since it's base e, yeah, we're gonna take the log of both sides to get to that exponent, but I want to take the natural log. I want to take ln of both sides. Anytime I see an e, it's a lot easier to use natural log. So why do I say that? It's easier to use ln with e, since the ln of e, which is what we simplified to, think about this. ln of e is just log base e, right? So e to what power equals e? It equals 1, right? So whenever I see e, I always use ln, because the ln of e is just 1. So it's almost like they cancel out, right? They're inverses of each other. Okay, so since I took the ln of both sides, this 2x gets to come out front. So I get 2x times the ln of e equals the ln of 10. But the whole reason I took the ln of e is because that's just going to cancel out. That's just 1. So that's gone. So I got 2x equals the ln of 10. So then the last step in solving for x, just divide both sides by 2. And if I didn't have a calculator, I would actually just leave it as ln of 10 over 2. Like, that would be a good enough answer. But with a calculator, in 3 decimal places, it's approximately 1.151. Okay, so properties of logs are down. We've got the power rule, the quotient rule, the product rule, and then we also did some solving with logarithms today. The whole point, solving with logs, is you can access those variables that end up being in the exponent. You just take the log of both sides, or you can take the ln of both sides, especially if you see an e. Okay, that's all for these notes. I'll see you in class.